We've seen that every derivative rule really is also an integral rule, since an indefinite integral is just an antiderivative. So what would the integral version of the chain rule look like? To see what it would look like, let's set up a situation where we have a composition, because that's what the chain rule is all about, compositions. So let's say we have a function capital F, and it's composed with, say, another function g. And just to have a little extra notation, let's introduce a new variable u for g of x. So u is just an abbreviation for g of x. And while we're at it, let's name the derivative of capital F. And let's name it little f, because that's what we usually do. So capital F of g of x, another name for that would be capital F of u. And one thing that we can do to get another equation that sort of expresses the same thing is on each side we can integrate and differentiate like this. So this left-hand side is the integral of the derivative of itself. So integral of the derivative of capital F of g of x, lots of parentheses here, dx. And on the right-hand side, f of u is the integral of the derivative with respect to u of f of u du. Now, it might look a little strange to have an integral and a derivative like this, but remember, since an indefinite integral is an antiderivative, all we're saying here is that if you start with this function, f of g of x, and you do a derivative and then you undo the derivative, you get f of g of x again. And then same thing on the right-hand side. If you start with f of u, you do a derivative, and then you undo the derivative, you get the same thing as f of u. So these are the same, these are the same, and these are the same because they're equal, and so these are the same. Okay. But what we can do now is, inside each of these integrals, we can actually evaluate the derivatives. The right-hand side one is a little bit easier. So we have a function f of u, and we're taking its derivative with respect to u, but that's exactly what this is. The derivative of capital F is just little f. All right. Now on the left-hand side, we're taking the derivative with respect to x of a composition. So to calculate this derivative inside our left-hand integral, we have to use the chain rule. And the chain rule says you take the derivative of the outside piece, which is little f, and then you put the inside into it, so little f of g of x, and then times the derivative of the inside piece, and the derivative of g is g prime. Okay, so now this probably doesn't look like much, but this is actually what we will use as the integral version of the chain rule. It's not usually called the integral version of the chain rule. Usually this formula gets called U substitution. U substitution. And the idea that the reason it's called that is because we had an integral that has some inside piece here, and we did a substitution, and we just called the new thing u. And the hope is that if you have a complicated integral that fits the pattern on the left, you can make it simpler by doing the substitution and instead calculating the integral on the right. So let's see how this works out with a couple examples. Okay, so we're going to find an antiderivative, so an indefinite integral of 2x times e to the x squared. And remember, what we're looking for is the integral of f of g of x times g prime of x dx. So this is what we're looking for, because that's going to be equal to the integral of f of u du. Okay, so to use this, what we need to do is figure out, well, what is playing the role of f, what is playing the role of g, what's playing the role of g prime, and what's playing the role of u. Of course, if we know what g is, then we know what u is. Okay, so to decide what part counts as f and g, notice that g is some inside piece whose derivative shows up outside. That's sort of the key insight here. So we're looking for an inside piece whose derivative is multiplied outside. Well, look, here's an inside piece, x squared, and the derivative of x squared is multiplying out here. And so that means that this inside piece should be g. So g of x is going to be x squared. Okay, and that's u. Right? G of x is just another name for u. So g prime is indeed 2x, and e to the x squared is e to the g of x. Okay, so we can rewrite this as the integral of g prime of x times e to the g of x dx. So we've identified g, so we can write it this way. And now we can use the u substitution formula. The u substitution formula says that this integral is the integral of just the outside piece, and the outside piece is the e to the something function, so e to the u du. And now hopefully, the hope with the u substitution is that once you're done with your u substitution, all of the x's are gone, and you only have u's. The hope is that this integral is easier to do than the one you started with. And this integral is easier to do than the one we started with. The integral of e to the u du, so an antiderivative for e to the u, that's e to the u, plus a constant. Don't forget the constant of integration. So our antiderivative is e to the u plus c. But if you look back at where we started with a function of x, right? An antiderivative of a function of x should produce a function of x. But here we have a function of u. So what we need to do is undo the substitution to get back to x's. And right, u is defined right here, so we can undo the substitution to get back to our x's. So u is x squared, so this is e to the x squared plus a constant. And there we are, we're done. Now this way of writing it out with g's and everything, and writing everything in terms of g prime, this isn't usually how you would write out this sort of substitution. So let me do this one again, but in a sort of more typical way. So we're starting out with the integral of 2x e to the x squared dx. When I look at this, I see that x squared is sort of the inside piece, so u should be x squared probably. I'm going to convert everything in this integral into u's, and so I need to know, in particular, I need to convert dx into du. So I need to know for this equation, this substitution equation, u equals x squared, I need to know what the corresponding equation is for differentials. So there's some corresponding equation that relates du to dx. And the corresponding equation is du equals, remember how you calculate differentials, you take the derivative of this, and the derivative of x squared is 2x, and then times dx. So this second substitution equation tells me that 2x times dx together make du. And then of course e to the 2x, that's e to the u. You can see we end up in the same place as we got before, but it's sort of compact, and I think it's a little easier to see what's going on here. And then at this point, you proceed to calculate the integral like we did before. So the integral of e to the u du is e to the u plus a constant, and then undo the substitution to get e to the x squared plus a constant. And we're done. All right, let's look at another example. Let's find the indefinite integral of x over x squared plus 1 dx. So remember, what we're looking for to do a u substitution is something that counts as an inside piece. For a fraction like this, I guess what you would usually want to treat as the inside piece is maybe just the numerator or maybe just the denominator. But remember, we're looking for an inside whose derivative shows up somewhere else. And if we treat x squared plus 1 as the inside, the derivative of x squared plus 1 is 2x, and there's an x. So it seems like taking u to be x squared plus 1, that seems sort of promising. So let's try this. Now we need to take differentials. So du is the derivative of this times dx, and the derivative of x squared plus 1 is 2x. Now we're actually missing a 2 here. We have an x, but we're missing a 2. One nice thing about these substitution equations is you can manipulate them algebraically just like any other equation. So in particular, we could take this second substitution equation and divide both sides by 2. That would give us 1/2 du equals x dx. And now we can group together x and dx. This equation tells us that x times dx together make 1/2 du. And then the remaining piece is 1 over x squared plus 1, but x squared plus 1 is u. So this x dx made 1/2 du because of our second equation here. All right, now we have done everything we can to get rid of x's and produce u's. And so hopefully there aren't any x's left, and indeed there aren't. So the u substitution, at least we were able to finish the substitution. Now the question is the resulting integral any easier to do than the one that we started with? And it is. It's much simpler. So we could start by moving this 1/2 outside of the integral because it's a constant multiple. So now we need to find an antiderivative of 1 over u, but that's natural log. So natural log of u. Plus a constant, don't forget the constant. And then just like last time, since we started with the function of x, we should end up with a function of x, so we need to undo our substitution. That's 1/2 natural log absolute value x squared plus 1 plus a constant. All right, so that's a u substitution for an indefinite integral. Let's look at a u substitution for a definite integral. So let's find the integral from 0 to 3 of the square root of 3x plus 1. So if we're going to use a u substitution, we need to identify something that counts as an inside piece. And since there's a square root, it seems like whatever is inside the square root should count as inside. So let's say that u is 3x plus 1, and du is then going to be the derivative of 3x plus 1, which is 3, times dx. And now we can do our substitution. But there's one extra thing to be careful about when we do a substitution for a definite integral, and that's the bounds of integration. So this 3 here as our bound, that's an x value, not a u value. And this 0 down here is also an x value, not a u value. So when we continue evaluating this definite integral, we need to be careful to not accidentally plug in x values for u, because they aren't u values, they're x values. Okay, so let's see what we can do. So this substitution looks like it's going to work, except this 3 that's on the right-hand side of our second equation, there's no 3 that we can put together with this dx over here. So let's divide both sides by 3. 1/3 du equals dx. Okay, now we can do the substitution. So our integral is from x equals 0 to x equals 3. Usually we don't write, when we write our bounds, we don't usually write what variable the bounds are a value for. But since we have u's and x's flying around, just for now I'm going to be explicit that these bounds are x bounds. Okay, so square root of 3x plus 1. 3x plus 1 is u, so this is square root of u. And then dx is 1/3 du. All right, so we got rid of all of the x's, except in the bounds. We'll come back to the bounds in a second. But in the integrand itself, we got rid of all of the x's, nothing but u's now. And this new integral, the integrand, is easier to integrate than what we started with. So this feels like progress, so let's press onwards. Now we need to find an antiderivative for the square root of u. Remember, the square root of u is u to the 1/2, so we can use the power rule for integrals. Also, let's move this 1/3 outside the integral. So 1/3 times, now we need an antiderivative for u to the 1/2. That's going to be u to the 3/2, but then we need a 2/3 out here, plus a constant. Don't forget. Actually, we're doing a definite integral, so we don't need the constant. Sorry about that. But we do need to evaluate at our bounds. So x equals 0 and x equals 3. Now it's tempting to just plug in 3 and 0 for u here, but remember, these are x values, not u values. So we can't plug them in directly. We need to get back to our x's first. So let's undo the substitution so that we have x's. First of all, these coefficients in front give us 2/9. Okay, then undo our substitution. U is 3x plus 1. And our bounds are from 0 to 3. And these are x values, and since our variable is back to x over here, now we can plug in our bounds. So 2/9, oh, and I missed an exponent here. This should be 3/2 right here. Okay, 2/9 times, plug in 3 for x, and you get 10, so 10 to the 3/2, minus, and then plug in 0 for x, and you get 1 to the 3/2, which is 1. And there we go. So there's our final answer. For definite integrals, there is another way to handle the bounds here. So in this case, I didn't change the bounds, but I went back to x's after I did the integral. But there's another nice way to do it. So the first couple steps are the same, but let's do one other thing to this integral. So the integrand is the square root of u times 1/3 du. The other way to handle the bounds is, instead of keeping your x bounds, switch the bounds to u values. Well, how do you do that? Well, look, here, the substitution equation that we chose tells us how to convert x values into u values. So for our lower bound, x equals 0, we get u equals 0 plus 1, so that's 1. So if our bottom x bound is 0, our bottom u bound is 1. And then we can do the same thing with the top bound. The top x bound is 3. We can plug that into our substitution equation to find the top u bound. So 3 times x, which is 3, plus 1, that's 10. So our top u bound is 10. And now the integrand is in terms of u. The bounds are also u values. And so now we can finish computing this integral and just forget about x completely and work only with u's. So doing an antiderivative, so move that 1/3 to the outside. Antiderivative of square root of u is 2/3 u to the 3/2. We're going from 1 to 10. And then these coefficients give us 2/9. And then plug in our bounds, 10 to the 3/2 minus 1 to the 3/2, which is 1. You can see both ways of doing it give us the same result, so it's really up to you which way you prefer to do it. Personally, if the bounds aren't too messy, I prefer switching to u values, but if the bounds are very messy, often it's a little bit easier to keep them in terms of x's. But it's up to you. Both ways will work.